This is the second in a series of videos that will culminate with you standing on the very forefront of human knowledge, the very edge where no other living eyes have seen before. Now, the previous video, Some Amazing Facts About Life, was a pretty broad overview of what constitutes pretty much everything that you see, the atoms and how they stick together to form compounds, and how one subsection of that is the biomolecules. Now, of the cellular life watching this video, well, excluding the water, of course, the biomolecules make up the majority of it. Now, they fall into one of four main categories: the lipids, which mostly make up your cell membranes, the DNA, which holds the sequences for making the proteins, of course, and finally the sugars, which mostly keep the system energetically ticking over. Now, the proteins are what I'm going to focus on today. So, what the hell's a protein, I hear you ask? Well, proteins are polymers of amino acids. Great. So what's an amino acid? Well, amino acids are made up of the four most common chemically reactive species in the universe. That's hydrogen, oxygen, carbon, and nitrogen. As by far the majority of this is hydrogen, most of these elements chemically exist as their hydrides. That is, oxygen exists as the dihydride, H2O, commonly called water. Carbon exists as the tetrahydride, commonly called methane. And for nitrogen, it's the trihydride, ammonia. Now, add a little planetary chemistry to get rid of some of that hydrogen and swap out a couple of those waters for carbon dioxide, and it turns out that what you've got left is actually more chemically stable as the amino acid glycine than as these constituent parts. Now, glycine is one of the most common amino acids. It constitutes about 7% of the proteins of your body. Indeed, this amino acid has now even been detected in comets in space. Now, pull off one of those hydrogens and replace it with one of a variety of side chains, and you get the other amino acids, and some of them like water and some of them don't. And string a load of those together in a specific sequence, and you get a protein. Proteins are the doers in the cells. Take, for instance, a protein that a lot of people have heard of, hemoglobin. That's stuff that makes blood red. Well, let me just highlight the glycine here. There you go. That amino acid has actually been found in comets. Okay, so proteins are the doers, you say. So what does hemoglobin do? Well, it increases the transport of oxygen in your blood by a factor of about 100. That is, without this protein, your metabolism could only run at about 1/100th of its current speed. Now, obviously, if this would happen to you now, you would just die because your metabolism is geared up to this high through flow of oxygen. However, you can equally see that if you had a competition between two organisms that didn't have this protein, the one that first evolved something that could perform a role along these lines would have a considerable selective advantage. And this is how evolution works at a molecular level. Now, the thing that first strikes you about hemoglobin, of course, is just how inefficient it looks. I mean, you've got a protein here with a molecular weight of about 20,000 that's transporting an oxygen with a molecular weight of about 32. I mean, damn, even a precursory inspection with a Mark I eyeball, you can see that there's an awful lot of protein and not much oxygen. And this is one of the hallmarks of evolutionary design, which is far more about existing things with some function being selected for rather than some sort of de novo design, which would probably be expected to produce something far more elegantly minimalistic. So how does hemoglobin achieve this factor of 100 increase in oxygen transport? Well, it's a balance of two factors. The first is, of course, it must favorably interact with the oxygen, otherwise how's it going to increase the solubility of oxygen in your blood? But the second is it must be able to release that oxygen. I mean, it's no good being able to bind oxygen really strongly if it never lets it go afterwards such that it can help work your muscles or whatever. Indeed, this is why carbon monoxide is so toxic, because it interacts with hemoglobin about 100 times more strongly than oxygen. And because you only need one carbon monoxide molecule to poison an entire hemoglobin molecule, you don't need much of the stuff to block up all of the oxygen carrying capacity of your blood and to kill you. Interestingly, when hemoglobin is poisoned by carbon monoxide, it goes very red, much redder than when it's bound to oxygen. And this is a trick used by many meat packing plants to make the meat appear redder, which people erroneously in this case associate with freshness. But this does very much highlight how evolution happens at a molecular level. I mean, just say, for instance, that there was a selective advantage to being able to move carbon monoxide through your blood. Hemoglobin would suck at doing this because it binds carbon monoxide far too strongly, but it would be a damn sight better than nothing at all. And evolution is a really good improviser like this. I mean, if this trait is strongly selected for in successive generations, you're probably only a mutation or two away from something that can bind carbon monoxide far less strongly, and therefore be a far better transporter of the molecule. Evolution is an absolutely fantastic repurposer of existing parts like this. It's far more of a tinkerer than it is a base-up designer. And this is mostly why these proteins come in these great families. So that's a quick summary about proteins. In the next part, we'll find out about protein folding and how it's possible for a protein, which would be expected to take well over 1 trillion times the lifetime of the universe to find its folded state at random, can actually do it in about 1,000th of a second.